All right, this problem says when a dilute gas expands, again, when they say dilute gas, what they're saying is the gas behaves ideally. Okay, so we can use all those formulas. Expands quasi-statically from 0.5 liters to 4 liters. It does 250 joules of work. So the gas expands and does work. Okay. For a gas, you can do PV diagrams. All right. And the work done is the area under the curve. You know them. Assuming that the gas temperature remains constant at 300 degree Kelvin. So it's an isothermal process. What is the change in internal energy of the gas? Okay. How much heat is absorbed by the gas? So, okay, so the first law of thermodynamics says Q minus W. Okay, so the work done is that okay. Okay, so when a gas expands, the temperature remains constant. In an isothermal process, the change in internal energy is zero. Okay, you guys remember for a ideal gas, it's the number of gas molecules times this is the internal energy given by that. So in an isothermal process, since the temperature remains constant, E is constant, and so delta E is zero. Okay. So part A, it's that. How much heat is absorbed by the gas? Oh, so since 0 minus Q minus W, Q is equal to W. All right, so that was a silly problem. It's not going to be on the exam. Well, it was an easy problem. No calculations. Yeah. So you just had to know the concepts there. All right, so in this problem, it says consider the process for steam in a cylinder shown below. Suppose the change in internal energy in this process is 30 kilojoules. Find the heat entering the system. Okay. So again, we are using the first law of thermodynamics. What they tell you change in internal energy is 30 kilojoules. So they give you that. They want you to find how much heat entered the system. So if you could find the work done by the system, then you could calculate the heat entering the system. And the work done by the system is just the area under that curve. Okay. So we'll calculate the work done, which is this area. And that area is the area of the triangle plus the area of the rectangle. Okay. So the work done is area A1 plus the area of a triangle is 1/2 base times height. Okay. This is in atmospheres. Base is liters, so 7 liters. And each liter is 10 minus 3 meter cubed. Height is, the height of the triangle is 30 atmospheres. And you got to convert that to pascals. Okay. Plus area A2 is 7 liters into 20 atmospheres. This height is 20 atmospheres. All right, so the work done is that gives you 10 to the power 2 3,000 times 7 is 21,000, divided by 2 is 10,500. And this is, again, 2,000 times 7, 14,000. It's 24,500 joules. 24.5 kilojoules. Okay. So the heat added to the system is delta E plus W is 30 plus 24.5 kilojoules. Okay, so again, this problem is based on the first law of thermodynamics. They give you the change in internal energy. They wanted you to find out how much heat is added to the system. You just had to figure out the work done by the gas when it expanded like that. And that was the area under the curve. Okay. Okay, this problem says 2 moles of a monoatomic ideal gas at 5 megapascals, so 50 atmospheres, and 5 liters is expanded isothermally until the volume is doubled. Okay. So again, they describe these processes. So for a gas, it's this is megapascals and volume in liters. Okay. So there's the initial and okay. So this is 5 liters and that's 10 liters. Then it's cooled isochorically. What does that mean? What does isochorically mean? The volume is constant, okay? So it's cooled. When you cool a gas, what happens? The pressure decreases, okay? So there's the, okay? That's the process. Until its pressure is 1 megapascals, okay? So this is 5, and that is 1 megapascal, 1, okay? The temperature drops in this process. The gas is now compressed isothermally. Okay, so now you're compressing it isothermally. Okay. Until its volume is back to 5 liters. So your volume is back to 5 liters. But its pressure is now 2 megapascals. Okay. Now, this drawing is not to scale, but anyway. Finally, the gas is heated isochorically. Again, isochorically means constant volume. Okay, there you go. To the initial state. Draw the 4 processes in the PV diagram. Find the total work done by the gas. Okay. What is the total work done by the gas? See, there's no work done under that curve, no work done during that process. The total work done is the area under this curve and minus the area under this curve. The total work done in this cyclic process is this area. Why is this work negative?
The work is negative because it's giving heat.
So And the convention was when the gas expands, the gas does work. The gas is compressing here, so you're doing work on the gas. The gas is doing negative work. Just like in integrals, when you take integrals from x1 to x2, x1 to x2, okay, if x2, for a positive function, if x2 is greater than x1, then this is positive. And if x2 is less than x1, then that's negative. Okay, so it's the same convention. All right, so the area in a cyclic process, and we saw this in lecture, if the cyclic process is clockwise, the area is positive. And if the cyclic process is counterclockwise, the work done in the cycle is negative. Okay. All right, so we'll call this work done in process 1 plus work done in process 2. Total work done, well, in this process is W1 plus W2. And you guys can look up, and what is the work done in this, during this process? 0. Work done here is 0, okay? All right, look up your formula nRT log V final over V initial plus, okay, so we'll come to the temperatures in a second. From the ideal gas law, PV equal to N PV equal to N okay, so nRT is P initial V initial log V final over V initial for process 1 plus P again, I'm mixing up notations, but you'll see this in a second. Log V final over V initial for process 2. All right, so for this thing, for this process, we'll take the pressure and volume over here. The pressure there is 5 megapascals, and the volume is 5 liters. Okay. And for this process, the final volume is 10 liters. The initial volume is 5 liters. Okay. Make sure we understand this, 5 megapascals. Volume is 5 liters. Log 10 over 5. The liters cancel, the units cancel. Okay, so that's just a ratio. Okay, I'm going to erase this. For this process, we know the pressure here was, or we know the pressure and volume here. So we can take that. So plus pressure there is 2 megapascals. The volume is 5 liters. Okay, for this process, what is the final volume?
It's going to be 5 over 10, right?
5 over 10, very good. So for this process, this was the initial state, 10 liters, and that was the final, okay, 5 liters.
And
So
that's why it comes out negative?
very good. Okay, so I wanted to point that out, and you noticed that, okay? And this is equal to, you guys know that, log 5 over 10 is equal to negative of log 10 over 5. And that's what Eli just said, okay? All right. All right, so now let's take care of powers of 10. That is 10 to the power 3, 25, 10 to the power 3, and that is 10, 10 to the power 3, okay? So 25 minus 10 is 15, 10 to the power 3, okay? So what did we just say? So the work done is 15 times 10 to the power 3 joules log 10 over 5. Okay. So the work done is 10 to the power 4 kilojoules. Okay. Now, in the next chapter, you'll see heat engines. Do you know an example of a heat engine?
The car?
Your car. Okay. Heat engines take a gas through a cycle. Okay. And you will want to know how much work is done in one cycle. Your generator is a heat engine, and so on. Okay. So you take a working substance through a cycle, and that's what we've just calculated, okay? The work done in one cycle. Do you guys remember we said internal energy is a state function? What does that mean? So here's the first law of thermodynamics. E is an internal energy, and we said that internal energy is a state function. So the internal energy of this gas just depends on its state. It doesn't matter how it got here, and so on. And it just depends on the state, okay? What else is a state function? The pressure of this gas is a state function, temperature is a state function, internal energy is a state function, and in the next chapter you'll learn entropy is a state function. It just depends on the state. Okay, so what this problem is going to show you is, if you go from here to there, the internal energy here is EA, the internal energy there is EC. So the change in internal energy is a fixed amount. It doesn't matter how you got there, like from here to there or from here to there. Okay. Well, so in this problem what you'll show is the heat added and the work done is path dependent. The heat added and work done is path dependent, but their difference is independent of the path. Okay. Okay, so we learned all of that in theory, and this problem will illustrate that. Yeah. Okay, I might just do half of the problem because I don't want to spend the rest of my life doing this problem. Okay. But you guys understand what we're doing? Okay. Okay, again, what is a state function?
It's a function that's half independent.
Something that just depends.
It depends on its
State.
how it got there doesn't matter.
Right, just depends on its state.
Physical state it's in right now.
Yeah, just depends on your state. Your age is your state function. Okay? Your bank balance is a state function. Okay? All right. So, consider the process shown below. in process AB and BC, AB and BC, 3,600 joules and 2,400 joules of heat are added to the system respectively. So along this path, you've added 5,000 joules of, 6,000 joules of heat. Okay? Okay, so Q is QAB, or let me be QAC equal to QAB, a little more specific, QABC. That is the path you've taken, okay, is equal to QAB plus QBC equal to 3,600 plus 20. Okay. All right. Find the work done in each of the processes AB, BC, and AD. Okay, I'm going to just do it for this path. Okay, what is the work done along AB? Now we're going to,
Zero, right?
very good, my friend.
But it stays.
Why is it 0? There's no area under that curve. Okay, plus BC. Okay, this guy is 0. It's an isochoric process. Okay, what is the work done along BC? It's 5 atmospheres. It's just this area, which is 5 atmospheres times 4 liters. Times 4 liters. That's 2,000 joules. Okay. So we've said that the heat added and the work done is path dependent. We know the heat added along this path, and we just calculated the work done along that path. Okay, so change in internal energy, A to C, is QABC minus WABC. Okay, so change in internal energy doesn't depend on the path, it just depends on the initial and the final point. Okay, these guys depend on the path taken. Okay, so this is 6,000 minus 2,000 equal to 4,000 joules. And what you should be able to show is that this will equal QADC minus WADC. That's the rest of the problem. And I'll let you guys do it. Okay? And if you have any trouble, go talk to Jeff. All right? You guys understand? Yep.
Are we finding the area only in respect to the volume? Or when you're
No, the area, when we found the area, the work done is this area. And that area is, well, that's a rectangle, it's the height times width. The height was 5 atmospheres, the width was 4 liters.
So if you were to find the area between A and D, or the work done between A and D,
Mm.
you'd only go from 2 atmospheres times.
Yeah, so
4.
you would be this area, which is 2 atmospheres times 4 liters. Okay. Okay. I'll do 2 more problems because I want to make sure we have a good lecture on chapter 4. All right, 1 mole of a dilute diatomic gas. Again, dilute just is telling you that all, what is it telling you? Very good. All the ideal gas laws apply, formula apply. Occupying a volume of 10 liters expands against a constant pressure of 2 atmospheres. So this is an isobaric process. Okay. What does it look like on a PV diagram? It's a horizontal line. Okay. So it's 2 atmospheres. If the temperature of the gas rises by 10 degree Kelvin, so delta T is 10 degree Kelvin. If the temperature and 400 joules of heat are added, what is the final volume? Okay. So initial volume is 10 liters. All right, so Q and they give you 1 mole of the gas. So N equal to 1 mole. Initial pressure is 2 atmospheres. Okay. So let's find the initial temperature. So PV equal to nRT. Initial temperature is initial. Okay. We have the initial temperature. We can calculate the initial temperature, and then they give you the final temperature. Well, it's 10 degrees higher, and then we can calculate the final volume. All right, so initial temperature is 2 atmospheres. Initial volume is one mole. Okay. So this works out to, that's 10 to the 2, 10 to the 3, 2,000 divided by 8. So initial temperature works out to 240.6 Kelvin. So the final temperature is 10 Kelvin higher, so 250.6 Kelvin. Okay, so the final volume is nRT final, or final pressure. Okay, and the final temperature, we know. What is the final pressure? Very good. 2 atmospheres, because it was an isobaric process. Okay. So 1 mole, 8 point. Okay, what should be the final volume? Is there anything you can say about it? It should be greater than 10 liters. All right, so what we'll do is, since we want it in liters, 10 to the, oops. So this will be equal to, V final is 8.314 into 250.6 into 200 into 10 minus 3 meter cubed. Did you guys see what I did? I took 10 to the 3 from here, brought that up there, and then the other 10 to the 2, I made that 200. Okay, and this number should work out to be greater than 10. Okay? So it did work out greater than, okay? All right. One more problem and then we'll take a little break. Okay, anybody remember what is an adiabatic process? What is an adiabatic process?
If you do work, all that comes from the internal energy, so it loses energy.
I'm sorry?
If you do work, all that comes from the internal energy.
Yeah, very good. Okay, so again, all these terms are with reference to the first law of thermodynamics. An adiabatic process is where you're not exchanging heat with the environment. Okay, so if you end up doing work, you're spending your savings. Okay, and if something does work on you, your internal energy increases. Okay, for an adiabatic process, this fellow is 0. Okay. So an adiabatic process on a PV diagram looks like this. PV, here's an isotherm, here's an isotherm. What is an isotherm? Temperature is constant and internal energy is constant. Okay, so let's say, so by the way, which is higher temperature among these two? So this, if you take the gas along this path, the temperature is constant. If you take the gas along this path, the temperature is constant. Which temperature is higher?
Or the one that's higher?
Huh?
The one that's higher?
Along which curve is the temperature higher?
Like the one that's higher.
Oh, yeah. So, yeah, you're right. So here's how you figure it out. PV equal to nRT. Okay. So if the temperature is higher for a given volume, the pressure is higher. Okay. That is higher. Okay. All right.
So the
So,
bottom is just a reflection of what happens up as you raise the temperature above it. So like the
So-
two lines there.
well, if you,
You've got the standard temperature, so it's as it changes, that's what the,
yeah, as the temperature rises, you're going from that curve, those are the curves you're transversing.
yeah, okay.
Yeah. All right, so you guys understand all of that. So here's an isotherm, here's an isotherm. And an adiabatic process is like this. Let's say if you were here and you expand, an adiabatic expansion happens. Well, you're doing work. You did work under this curve. You did work. Where did that energy come from? From the internal energy, and so you cool down. Okay, so that's an adiabatic process. Now, here's the deal. I mean, so here's a process. Here's an isothermal process. So in this process, can you say anything about that process? So we like to say stuff like, you guys remember when you saw the pool rack being broken? That was a complicated process. Do you remember anything that was constant in that process?
Momentum?
Very good. And kinetic energy and stuff like that. So that's the kind of stuff we like to say. We observe processes and we want to say what is constant in that process. Okay? So you're saying something about the process. In an isothermal process, temperature is constant, internal energy is constant. Okay, so we were able to say that. Okay. In an adiabatic process, this fellow is constant. Okay. So you can take at every point, take any point on that curve, take the pressure at that point, volume. What is this fellow?
Gamma?
Gamma. And do you guys remember what gamma is? I'm sorry?
The wavelength or?
No. Gamma is the ratio of specific heats. Okay? All right. So, and remember, gamma tells you how complex the molecule is. For a monoatomic gas, for the noble gases, gamma is 1.67. For a diatomic gas, gamma is 1.4. And a more complex gas, gamma will be smaller. Okay? So more complex a gas, smaller is gamma. Okay? Anyway, the important thing is along this curve, PV to the power of gamma is constant. Okay? There's another thing you can say, TV to the power of gamma minus 1 is also constant. But you just use the, okay? So those are two things that are constants along that curve. All right, so it tells you, so pressure and volume measurements of a dilute gas undergoing a adiabatic expansion are shown below. So they give you various values, various points along that curve. Okay. Determine gamma for this graph, for this gas. Okay, so what we'll do is, we know that, okay, so let's say we take this point, we'll take this point. I'm going to pick easy points and this point. Okay, so what we know is P1 V1 to the power gamma should equal P2 V2 to the power gamma. Okay, so P1 is 20 atmospheres. And again, see, since this is an equation, we don't have to convert, we can keep these units. Okay, we don't have to convert them to SI units. So this is 20 atmospheres. V1 is 1 liter to the power gamma equal to P2 is 1 atmosphere and 8.4 gamma. Okay. So 8.4 to the power gamma is 20. Yep. And whenever you want to solve for something in the exponent, what is it that you do? I'm sorry? Yep, exactly. Okay, so you'll take the log of both sides. So log, doesn't matter what base you take it to, 8.4 gamma equal to log 20. So this works out to 1.4. So what does that mean?
That should be constant for each point.
No, so the value of gamma, remember gamma is 1.67 monoatomic gas. Okay, gamma equal to 1.4 diatomic gas. Okay, gamma less than 1.4, it's a more complex gas. Okay, complex molecule. All right, so that's the kind of information you can extract from those tables. Okay. All right, guys, so take a